Hello everyone. Today I start our second remote class. First, I will talk about some more examples of mathematical induction. Let's consider the following. Use induction. We want to use induction to prove that n cube minus n is divisible by 3 whenever n is greater than or equal to 1. Recall that in mathematical induction, we take a variable and prove by induction on that variable. Here we just have n and we prove by induction on n. The base case is the case n equal 1. So for the base of the induction is just set n equal to 1, then we have 1 minus 1 equals 0. And 0 is divisible by any number, so this is correct. Now the inductive step. Inductive step, we assume that whatever we want to prove here, this statement is true for n equal k, and we prove it for n equal k plus 1. Therefore, induction hypothesis is that k cubed minus k is divisible by 3, which is equivalent to saying that it's 3 times L for some L. We must prove that k plus 1 over 3 minus, minus k plus 1 is again divisible by 3, which means 3 times some L prime. All right, now this is again a very simple example, and we just expand the here the left hand side of what we want to prove. If we do that expansion, we get the following. This is equal to k q q squared plus k plus 1 minus k plus 1. So if we just reorder these terms, we get k cube minus k plus 3 times square minus k. But we know by induction hypothesis that k cubed minus k is 3 times L. So I just put it there. Therefore, this will be 3 times L plus 3 times L prime. So 3 times L times k squared minus. Now inside here it should be plus. And obviously this is again 3 times some L prime. And we showed that if k cubed minus k is 3 times some L, then k plus 1 cubed minus k plus 1 is 3 times some L prime. Therefore, we proved that for all n greater than or equal to 1, n cubed minus n has to be divisible by 3. And actually, there is a proofs of this fact, which you can find in the book, but this is an example of mathematical induction. Okay, now let's go to another example. This example is a little more less simple than previous examples, and it's about the subsets of a finite set. We want to show that if S is a set of an element, then it has n subsets. And we want to prove this statement using mathematical induction. And obviously, again, we have to use induction on n. And here, the base case is n equal 0. Because there are sets of 0 elements, so the base case is n equal 0. For the basis set, n equals 0. But the only set that has 0 elements is the empty set, and the only subset of an empty set is itself, which is an empty set. And therefore, it has one subset, and 2 to the 0 is also 1. And therefore, the basis step is correct, it's true. In the inductive step, we have to assume our statement for k, for a set of k elements, and prove that for a set of k plus 1 elements. We assume that a set of k elements has 2 to the k subsets. And then we want to prove that a set of k plus 1 elements has 2 to the k plus 1 subsets. We want to prove that if S is a set of k plus 1 elements, it has to do the k plus 1 subs. Let's take such a set S, and because k now is greater than 0, there is some element in the set S. Let A be an element in S. I want to divide or partition the subsets of S into two classes. Those subsets which have A in them, and those subsets which don't have A in them. So let me draw a figure here. So imagine this is all subsets of S. I can divide all the subsets into two parts, which one part contains those subsets contain A, and here the other part is subsets which do not contain A. For example, the set which has only A in it is in this part, and the empty set is in this part, and S itself is in this part. So all of the subsets of S I can put into one of these two parts. Now, the part which is subsets which do not contain A, now these are actually the same as all the subsets of S, the set S minus A, correct? Because every subset of S minus A, it has to be in here, and every subset here is a subset of S minus A. Therefore, because also S minus A has k elements, by induction hypothesis, we know that it has 2 to the k subsets. Therefore, here there are 2 to the k subsets in this set. Okay, now we're going into the other part. These subsets here are contained A. Now I claim that every subset in this part is obtained from a subset in here by adding A to it. And therefore, it's like that we have an operation from this part into this part, which is a union with A. So it takes T, which is a subset which doesn't have A in it, into the subset T union A. And it's like sending sending subsets into subsets, and it is easily seen that if two subsets in this part, T and T prime, are different, then T union A and T prime union A are different. And therefore, this is an injective function of the subsets here into subsets here. And also clearly every subset in here, because it's contained A, is obtained by the union of something here with A. And this argument shows that there is a one-one correspondence between all the subsets in here and all the subsets in here, and therefore the number of subsets in this part is also 2 to the k. And because these are disjoint sets of subsets, so they don't have anything in common, every subset either has A or doesn't have A in it, the total number of subsets is the sum of all the subsets in these two parts, which is 2 to the k plus 2 to the k, which will be 2 to the k plus 1. Therefore, we have proved that the number of all subsets of S is k plus k, which is 2 to k plus 1. And this was what we wanted to prove. Note that we use the induction hypothesis to argue for the number of subsets which don't contain A, and then show that those which contain A also have to be the same number of subsets, and therefore the total number is multiplied by 2. Okay, we go to the next concept here, which is strong induction. Recall that if we want to prove using mathematical induction and a statement involving n, like Pn, so Pn is a statement, for example, a formula involving n, and we want to prove Pn for, let's say, n greater than 0, then we had two steps. The base step, which assumed, actually we checked P of 0, P of 1 in this case, and then the inductive step, which assuming pk, we prove pk plus 1. Now, a strong induction differs from the ordinary induction in that in the inductive step, instead of assuming pk is true, we assume that all of the p1, p2, p3 up to pk are true, and we make use of that assumption. So essentially, it has a stronger assumption than the ordinary induction. And it is not essential for proofs, but it simplifies some of the more complex proofs using induction. Yeah, so let's first simplify this here to say n greater than or equal to 0. Then a strong induction here has two steps, showing that p of 0 is the base step, just like the ordinary induction. But now in the inductive step, assume that P 0 and P of 1 and P of 2 and all the way, and P of k minus 1 and P of k are true, then prove P of k plus 1. So we make a stronger assumption about, we make our induction hypothesis stronger. So that's why it's called a strong mathematical induction. And it's clear that the same logic that works to show that mathematical induction is a valid way of proving statements also works here, because we already have shown that our statement is true for all the values before k minus 1, and therefore we can assume that we can use this thing that we have already showed. Let's do an example of an application of a strong induction. Show that if n is an integer greater than 1, and n can be written as a product of prime numbers. This is called the fundamental theorem of arithmetic, but it's actually quite very easy to prove using strong induction. Again, we have two steps, and the base step is the smallest number greater than 1, which is 2. N equals 2. But when we say a product of prime numbers, when a number is prime, is obviously a product of prime numbers. So this is by assumption or by convention. So when the number itself is prime, you think of it as a product of prime numbers, and therefore the 2 is prime and the base step is checked. Now we go to the inductive step. The inductive step, now we want to assume that we have the statement for all of the numbers less than and equal to k. Therefore, we assume that 2, 3, 4, all the way to some k can be written as product of primes. And we want to show that k plus 1 can be written as product of primes. We must show that k plus 1 can be written as product of primes. But this is actually quite easy. Why? Because either k plus 1 is a prime or not. So if k plus 1 is a prime, then as the case of 2, it can be written as a product of prime numbers. So if k plus 1 is prime, we are done. Otherwise, k plus 1 can be divided by some other number like m. Otherwise, we can write p to be, k plus 1 is m times some q, where m is greater than 1 and less than k plus 1, and also q is greater than 1 and less than n plus 1, because that's by definition of not being prime is that you can be divided by some other number. Now, by a strong induction hypothesis, we know that both m and q, because they're at most k, I should write here k plus 1. By induction, strong induction hypothesis, we know that because m and q can be at most k, then they can be written as product of primes. But k plus 1 is product of them. So therefore, it can be written also as product of the primes in M and the product of primes in Q. Therefore, by strong induction hypothesis, we know that M and Q can be written as product of primes, and k plus 1 is the product, and also be written as product of primes. And you see that using strong mathematical induction, this proof becomes very simple and nice. In the next section of the book and of the course, we learn about recursive definitions. We've already seen a recursive relation and how to define sequences by a recursive relation. And here we also want to define other structures recursively, like functions, sets, etc. And then when we define some structure recursively, we can prove some property for that structure using a proof similar to an inductive proof or to a mathematical induction. That is called a structural induction. I will start first by showing an example of a recursive definition of the picture. So here is a picture in your book, which you should imagine it as recursively defined. So how is this picture recursively defined? First, actually, this is quite a confusing picture that the book uses, but one way of seeing it, this picture as recursively defined is by first assuming that this sequence of somehow pictures that lie inside and the same picture, they just go to infinity, so they don't stop here, they just continue to become smaller and smaller and smaller. Then the picture first starts by is essentially just the material here. So that's the first picture. So let me then show that. All right. So this is the first picture, consists of the material here. Then you, to define the second picture, you somehow squeeze this one and put it inside the smaller square in the middle. And then if you do that, you get this picture. All right. And now again, you squeeze this picture that you have and put it inside this smaller picture. And then you will get something like this. And you continue like that until you have infinitely many, or as large as you want, or if you can say you can continue to infinity, so it's not the actual picture, it would be an imaginary construction that goes to infinity and has infinitely many of these pictures inside each other. Okay, the first structure that we want to define recursively is just a function from natural numbers to natural numbers. F from n to n is just a function from natural numbers to natural numbers. Any recursive function is defined using two steps. First, define f for base values. Base values are the smallest values where we need the function to be defined for them. And in the second step, we define the function value of function at arbitrary n in terms of f n minus 1, f n minus 2, f 0. So now how many base values we would need depends on the recursive relation and how many lower terms it involves. So you realize that this is just similar or exactly the same as the recursively defined sequences. We are just now looking at them as a function. So as an example, let us define f of n as follows. So I will define f of 0 to be 3 and f of n plus 1 to be f of n prime f of n plus 3. You see that in this definition, we have some one base number which is 0 because we define f of n plus 1 only in terms of f of n. So one lower than n plus 1. So we just need to define 0. So if here we had fn plus also fn minus 1 in this relation, we needed to also define the base number 1, the function value for 1. And therefore, in this way, we can actually define functions recursively, just like sequences. And we now using mathematical induction, an extension of an mathematical induction, which is called a structural induction, we can prove properties or statements regarding recursive functions. How is that? It's actually very similar to the ordinary induction, and I show an example of it here. Let f of n, the sequence of n, or you can just, instead of f underline n, we can just write f of n. It doesn't matter. So f of n is the Fibonacci numbers. So recall that the Fibonacci numbers are defined as follows. So we have base values. F of 0 is 0, f of 1 is 1, and the recursive relation is that f of n is f of n minus 1 plus f of n minus 2. Fibonacci numbers have a lot of applications in biology, etc. So it's important to prove properties of a function which is defined recursively like this. The property that now we want to prove is the following. Show that when n is greater than or equal to 3, we have f of n greater than a to the n minus 2. Here a is the following. A is equal 1 plus a square root of 5 divided by 2. Therefore, the goal here is to prove that f of n with this recursive definition for n satisfies the relation f of n greater than a to n minus 2 for all n. Now, very similar to the mathematical induction, we have two steps. One, the basis step. In the basis step, we need to check the equality for all of the base values. So this is one of the differences with mathematical induction, where we had only one base value. Here we have two, and we need to check for all the base values. But now note that the base numbers are not 0 and 1 because we are going to prove for n greater than or equal to 3, and we should start from 3 and go higher up by 2 to check all the base numbers. So our base cases are n equal 3 and n equal 4. Now for n equal 3, we have that actually we must show that f of 2 is greater than a sorry, for 3 should say that should show that f of 3 is greater than a to 3 minus 2 is a. This is very easy to check because we have the following. We have f of 3. If you use the recursive definition, you will see that f of 3 is 2, and this is actually greater than a because a is, so square root of 5 is less than 3, and 1 plus square root of 5 divided by 2 is less than 2. So this relation is true, and we checked one of the base cases, and the second base case is f of 4. If you check f of 4, is actually 3, and we have that a to the power 2. If you calculate this number, it will be the following. So a squared is 3 plus the square root of 5 divided by 2. And again, it's usually check that this number is less than 3, which was f of 4. And therefore, we also check our base case for n equal 4. The next step is the inductive step. In the inductive step, we use the recurrence relation to prove our statement for f of n if we know that our statement is true for f of n minus 1 and f of n minus 2. Therefore, we assume that f of n minus 1 is greater than a to the n minus 1 minus 2 is n minus 3, and f of n minus 2 is greater than n to n minus 4. This is our assumption, and we must prove that f of n is greater than a to minus 2. But we know that f of n is equal to a of n minus 1 plus f of n minus, and we already know that f of n minus 1 plus f of n minus 2 is greater than by the inductive hypothesis. We have proved our statement for all numbers less than n. So we can say that fn minus 1 is greater than a to the n minus 3, and f of n minus 2 is greater than a to the n minus 4. And you see, okay, this equation here, so let me just erase this thing that we want to show. Let me erase a minus 1. Sorry, a minus 2. All right. And the summation of these two terms is greater than summation of these two terms. And now we want to use a property of this number a. And I will write that property here. And a is a solution to the equation x squared is x plus 1. Therefore, so this is easy to check. So you check that a squared, a satisfies this equation. Therefore, we have a squared is equal to a plus 1. Now from the relation, you just multiply this relation by a to n minus 4, and we get the following. That a to the n minus 2 is equal to a n minus 3 plus a to the n minus 4. So I write this equation by multiplying this equation here by a to the power n minus 4. But now this equation tells us that a to the n minus 3 plus a to the n minus 4 is equal to a to the n minus 2, and therefore we can just write in place of these summation a to the power n minus 2. And this is what we wanted to prove, that f of n is greater than, so f of n is greater than a to the n minus 2. Now, I repeat again what we've done here. So we had a recursively defined function, and we wanted to show that that function fn satisfies this inequality for n greater than or equal to 3. Now, because the function fn has a recursive relation based on two previous values, f of n minus 1, f of n minus 2, it's essential to have a correct proof that we check in our basis step for the first two smallest numbers, which are n equals 3 and n equals to 4 in this case. And we check the relation or an inequality for the two base values. And then in the inductive step, we assume that inequality is true for f of n minus 1 and f of n minus 2, and we showed that it must be true for f of n. And it follows now that the inequality has to be true for all the numbers n greater than or equal to 3. And the reasoning why this is the correct way of proving is exactly similar to the reasoning which I said about why the usual mathematical induction is a correct uh, proof method. And so I finished this session with this example.